So let's see here. Let's look at the picture. We know here's some theta. This is b, this is a, this is r, which is a squared plus b squared square root, which is also the norm of z. This is the point z, right? We also know then that z bar, its complex conjugate, is going to be here. This will be by symmetry minus b. This will still be a. This is theta bar. I'm claiming that theta bar, which is complex theta, is just the negative of theta. Well, we should really prove that. Incidentally, what is this right here? Okay, so this is also r, which is the norm of z bar, and this is still going to be a squared plus negative b squared square root. Negative b squared is b squared. This is a squared plus b squared square root. So let's think about this. We know then that the tangent of theta bar is equal to the sine of theta bar over the cosine of theta bar, and this is minus b over a. Right? So we also know that sine is an odd function and cosine is an even function. That is, we know that the sine of negative theta is equal to the negative of sine theta. We know that the cosine of negative theta is equal to cosine theta. The even functions kill it off. So what do we have here? This is the tangent. Tangent theta is an odd function. So tangent theta is an odd function. So I can really write this like this. I know that sine of theta is b over a, or I'm sorry, tangent of theta, which is sine over theta over cosine of theta, is b over a. That means I can do this. I can multiply both sides by negative 1, right? It doesn't change anything. So, but this can be translated into the sine of negative theta is equal to minus b over a. This will be cosine theta. So this is true. I just multiplied both sides by negative 1, took the negative and drove it through the sign, which I can. Now, this, however, remember that cosine of negative theta is the same as cosine of theta. So this is the same as the cosine of negative theta. This is the tangent of theta bar. And this then is equal to minus b over a, which is sine of negative theta over cosine of negative theta. I was just thinking about this. I kind of just did this on the fly, and this is obvious, and I should be able to do this on the fly, but I don't explain it very often, and the more times you explain things, the better the explanations get. Hopefully you will believe here that if z equals r e to the I theta, then z bar equals r e to the I minus theta, which we write as minus I theta. Okay. And hopefully I've made a good case for this. Those of you who are more interested in just making this work, this is kind of what you need to know. Hopefully there's somebody who thought that was nifty. Okay, so anyway, I'm trying to show that these things are in fact equivalent, and the reason I went into this was I want to do this. If z is equal r e to the I theta, we know that z bar, or the complex conjugate, is r e to the minus I theta. I need to show that this representation still yields that the norm of z, which is z times z bar, which is the square root of a squared plus b squared, is the same if I use this representation. Right? So the norm of z is going to be z, which is r e to the I theta, times z bar, which is r e to the minus I theta, times the square root, right? Or taking as square root. This is the same as r squared e to the I theta times e to the minus I theta. This is the square root of r squared e to the I times theta minus theta. Hopefully you can see that this is 0. This is e to the I 0. This is just e to the 0. This is 1. This is the square root of r squared. This is r. But we already know what r is. R is a squared plus b squared square root. Okay, let that sink in a little bit. That these representations that they work and that they're consistent is obviously a big deal. Okay. So now, there's a reason why I'm spending so much time with this, and we're going to get there now. The pretty cool stuff is coming. So remember that sine and cosine are periodic functions. I guess I'll do this in a bit. Ooh, I got yellow. I'll use this in a bit. Remember that cosine x plus 2 pi is equal to cosine x, and sine of x plus 2 pi is just equal to sine x. These are periodic functions with period 2 pi. So if I have this number, z, which is a plus ib, and I'm going to write this as r e to the I theta, I can write this as r e to the I parentheses theta plus 2k pi. Basically where k is an integer here. Because what's going to happen is that this is just saying this is r times cosine theta plus 2k pi plus I sine theta plus 2k pi. As you know, these are, for every value of k that's an integer, these are going to come out exactly the same because these are periodic functions. So this gives me a number of ways to represent each particular complex function. Okay, so what did we just say? Remember when we were talking before, when we multiply complex numbers, if we multiply z1 times z2, we end up multiplying their norms together, their radial lengths, so to speak, if you're thinking of it in those terms, and then we're adding the angles. Let's see that that's actually true. So if we let z1 equal r1 e to the I theta 1, and z2 equal r2 e to the I theta 2, then z1 times z2 is going to be this, r1 e to the I theta 1 times r2 e to the I theta 2. This is r1 times r2 e to the I, okay, I theta 1 times, I guess I'll do this in 2 steps. Theta 1 times e to the I theta 2, right? So I just organized things a little bit. Here's why I wanted to take the second step. Sometimes students don't see this right away, and we only have a minute left. But this has the same base. This is am times an. This is a to the m plus n. I'm going to do that right here. This is r1 times r2 e to the I theta 1 plus theta 2. And we'll be right back.